here, we know that stress X at point alpha is equal, if we apply the formula, we're equal to minus mz over izz multiplied by positive y. So when you multiply all this at stress X at point alpha, we know that this will be under what? Compression. And visually, when we see it, yep, alpha is compression. Okay, this case where I wrote down alpha is equal to y is positive. That is when we apply the formula. Okay, now if we look at point beta now, right? At point beta, y is negative relative to the centroid and is pointing away from the center of curvature. Right? Why negative? Because pointing away from the center of curvature. Right? So when we apply the formula, we have stress X at point beta. So now what we get is equal to minus mz multiplied by minus y divided by what? Izz. So minus, this will become what? Positive, which correspond to tensile. Okay. Now this is applying the formula, if you remember. If you don't remember, I have solved a lot of problem with multi-axis bending. The easiest method is this. Okay, let me tell you what's the easiest method. The easiest method is by over here, the head of the moment vector okay, is always compression. The tail of moment vector is always in what? Tensile. Just remember that. Okay, you don't need to like center of curvature positive, away is negative. No, just visualize based on the moment vector. All right, the head of the moment vector is in compression, the tail is in tensile. So I'll give you another example. Okay, so what if now, right? Transformation is now. What if now? Okay, there are some questions that are really tricky. So what they do is okay. We are going to switch over. Okay, and now this is my y, and I'm going to call this my x now, right? And then x to y, and then this is my rotation, well, z. Some questions are meant to trick you, okay? Then when you start looking at the formula, I'm not so sure now, right? Okay, so now I'm still going to draw right the beam, right? Again, one side is on pin, the other side is on roller. Now what I'm going to do, right, is I'm now going to put P in the opposite direction. Okay, and then I'm still going to call this our point A, our point B, and our point C. And in this case, this is our point alpha. In this case, this is our point beta, right? So when you have this, right, the deformation pattern now will look like this. Right, so this is our deformation pattern. So at this point over here, this is our alpha prime. In this case, this is our beta prime. And if we were to look at our moment vector now is in this direction. Right? So this is in compression. the head of, so moment about Z, right? Moment about Z, right? And the tail end is in what? Tensor. The tail end is in tensor, right? So now when you apply the formula, right? Or when you look at the moment vector, you will say that alpha, right? Or stress Z at point alpha now is equal. So alpha is in what tension? So it's positive. So you know it's mz over izz now multiplied by what? Multiplied by x. Okay. And if you look at stress z at point beta now, it is equal, is in compression because the head of the moment vector, right? So alpha or beta is in the compression, whereas alpha prime is in the tensile, beta prime is in the what? In the compression. So you know that is equal to minus mz over izz multiplied by what? Multiplied by x. Okay, so this is by right visualization. If you want to use the formula, you can do the same. So you now know that now down here is the center of curvature, right? And then anything pointing. So if we were to draw the geometric centroid, if we were to sketch the geometric centroid, right? So now when x is pointing towards the center of curvature, now x over here is positive, is pointing away from the center of curvature. X is what? Negative. So now if we were to apply the formula, right? So we will have stress Z. So now for this case, our what? Our x at point alpha, x is what? X is negative. So when you apply the formula, stress Z alpha is equal to negative mz over izz multiplied by negative x. So that is why negative and negative, this will give you what? Tensor. Likewise, at beta, x is positive. You have stress x of beta. So this will be equal to minus mz over izz. And then the x will now be positive, right? So this, for this case, it will be in what? Compression. Okay. So the easier thing to do, so note, more easy to learn, note head of moment vector is in compression. Okay. Tail of moment vector is in what? Tensor. Okay, just remember that. Right. So we just look at what we mean by centric symmetrical bending. Now, the next thing I'm going to look, or I'm going to do now, is I'm going to draw a structure now that is under eccentric bending. Okay. So let's look at eccentric bending. Knowing the words, what it means, and physically see what it does are two very different things. I want you to see that. Okay. So the next thing we want to do is we are going to look at eccentric, symmetrical, bending. So in eccentric, symmetrical bending, the moment is applied in one axis only. Okay, one axis only. And accompanied by a axial load. Okay, it's accompanied by axial load. So now, how does this look like now? Okay, so a typical example. Again, I'm gonna base on our transformation x and y and rotation about z. Okay. So now let's assume that the structure is built in on one end. Okay. So now the structure is built in. So this is our point A, and this is our point B. And then I'm going to sketch our geometric centroid. So this is our geometric centroid. So now the load is applied in such a way, right? Applied in such a way that is acting on the geometric centroid, right? And is doing this. Okay, so this is our P. And over here, we have a theta. So if we resolve in the x and y component, we are aware now that we have to break this into two components. So we know that we have one component over here. Now this is our px component. And then we have the other component, which is our py, right? So for this case, right, the formula that we are going to apply now is stress x is equal to px over a. Now over here, we will deliberately put px over a because px is acting in the tensile direction relative to point A, right? It's stretching point A. And then if we're going to apply the formula, then if that's the case, we are going to follow the formula. So usually the generic formula is minus mz over izz multiplied by y. Okay, so that is the formula. So now, if you look at a structure like this, okay, failure will occur at point A. Okay, failure will occur at point A, and this is because the applied moment which is mz at point A is highest. Why is that? Okay, so if we call this distance from here to here L. Right? if this is L, right? So moment about Z at point A is equal to Py